elasticity of one-dimensional continua and nanostructures, which is a nice combination, I guess, of topics that every engineering student should know from the very first semesters, on the one hand, when it concerns beams and rods, with more advanced topics that are related to nonlinear continuum mechanics, plus atomistic modeling. So our lecturer is Professor Ajit Kumar. He's too modest to put his name here, but here you can see his name. So Professor Kumar studied mechanical engineering, like most of you, I guess. Initially at the IIT, these are the most prestigious institutes in India, Indian Institutes of Technology in Kharagpur, till his bachelor degree. And then he moved to the greatest country of all, not at that time, but nowadays, to the Cornell University to pursue his Master of Science there. And then also later his PhD, which was, I suppose, already a little bit in this direction here of multiscale modeling.
It was.
And after that, he pursued his postdoc in the University of Minnesota. So in total, this was like a 6-year stay in the greatest country. And since 2012, until now, he is a professor at the renowned Institute of Technology of Delhi in India, in the mechanics department.
It's applied mechanics.
Applied mechanics department. So, and we have, as the university here in Erlangen, together with the Indian Institute of Technology in Delhi, we have this 4 years exchange program that is funded jointly by Indian and German institutions, which has a lot to do with exchange, of course, and also education and lecturing. And in this regard, we planned this little series here on topics that are in the center of the research of Professor Kumar on the one hand, and on the other hand also fit nicely in various activities here in our environment, not only here at the chair of mechanics, but also broadly in the technical faculty and beyond. If you have read the flyer or the poster, you already got some of the motivation that whatever we do can also be applied here in the area of DNA and various more biological questions, but also, on the other hand, it has quite strong technical application if you think in terms of nanowires and things like that. So with that, I would say I hand over the stage to you, Ajit.
Thank you.
Enlighten us.
Sure. Okay, so a very good morning, everyone. So before I start, could you please sign on this sheet? So I'm just passing it here. So as Professor Steinman said, I am Ajit Kumar, and we are going to have this lecture on elasticity of one-dimensional continua and nanostructures. So we will, as you will see later on, we will study the one-dimensional structures both at continuum and at the nanoscale. So how the theory looks like at the continuum scale and at the nanoscale, and how can the two theories be bridged together. So that's what I say here, a multi-scale viewpoint. And I'll have later on several slides which will tell you what are the various applications of this theory. Okay? So let me just go to the next slide where I talk about where we come from. So, here we are. So we are 3 people here. I also have 2 very good friends of mine, Prakhar Gupta and Smriti Singh. They are working with me at IIT. So I think you will also hear from them. And in fact, some of the things that we will learn here has been, I worked together with Prakhar as part of his PhD. So, so he can tell a lot about, he can talk about it in a very nice way, because that's his work. Okay. So, here is a profile of IIT Delhi. So, well, the picture that you see here is the main building of IIT, and it's a very green campus, perhaps not like what it is here, but it is of course a green campus. If you see how Delhi is, you walk around in Delhi and you go to IIT Delhi, it's two different worlds. Yeah. So, some statistics, we have total 8,000 students. That's very less compared to what you have here, I guess. 40,000, is it?
Yeah, but the technical faculty is like 12.
12,000, okay.
So
more or less the same then. Okay.
could shrink maybe to that number.
Okay. Okay, so UG students we have, so bachelor's students we have about 3,500, and postgraduate, which includes PhDs, we have about 4,000 students, and the total faculty is about 460. Number of PhDs that graduates from IIT Delhi each year is about 250, and we have awarded about 45,000 degrees till now. Of course, that includes bachelor's, master's and PhDs. Okay. And the way IIT started, once we got independence from Britain, then we had our Prime Minister Pandit Nehru, who wanted to gear India towards technological development. So, that was his thought, that let us establish institutes of technology, renowned institute of technology, on the lines of what we have in Germany or in the US. So, that is how it started, and the first IIT that was started was IIT Kharagpur, from where I graduated, and that was purely, so it's like an indigenous IIT. So, it was purely made from Indian government, and of course, after that many more IITs came with the support of other countries, like IIT Kanpur from the support of United States, and we have IIT Madras, which was supported by Germany, and likewise there are many more IITs. Okay, so these are centers. We have centers at IITs, departments, schools and centers of excellence, and the one that I come from, applied mechanics department, that you see over there, the first one within the departments. Okay, so we have various departments: applied mechanics, biochemical, chemical engineering, chemistry, civil engineering, computer science, electrical, humanities also. So, it is not just technology, we also have humanities, management, mathematics, mechanical, physics, textile. Okay. And we also have centers which are more focused towards research. So, in departments we have undergraduate program where we teach and also do research, but we also have centers which do not have undergraduate program. They only have postgraduate program, and they are more focused towards research. Okay. Then we also have centers of excellence. So, these are the ones which keep changing, depending upon funding scenario and depending upon interest. These are volatile. So, it may exist for 5 to 6 years, and then depending upon interest it may continue or may get shut down. Okay. All right. So, and the department that I come from is applied mechanics. It's very much like the chair that we are here in. Hi. So, we work in solid mechanics, fluid mechanics as well as material science. All right. Okay, so that was about IITs. So, as I told you, this lecture is about theory of one dimensional continua. And most of you must have learned in your undergraduate course about beam theories, right? Has anyone not learned about beam theory? Is anyone not from mechanical engineering? Not from mechanical engineering, anyone? Okay, so that's really good. So if you all have learned about beam theories, that's really good. It's going to make my life much easy. Yeah. So beam theories, as you'll see, its application is very limited. To be very precise, the rotations of a cross section in beam has to be very small. The cable that you see here, it's also a one-dimensional continua. And if you want to apply beam theory to model this cable, then all that you can do is this. And if you want to do something like this, say large rotations are involved, goes like this, you can't use beam theory. And then you have to use what is called theory of elastic rods. Okay? So that's what we are, we will also learn something about beam theories, but then it will be mainly focused on theory of elastic rods, where we want to handle these large deformations, large rotations. Okay? So let me give you some interesting applications of this elastic rods. As you see here, the one that I demonstrated just now is in mechanics of cables. On the leftmost side that you see is marine cables, and you can see there is looping of such cables. Then you have this telephone cord, and you have just a wire, just a cable. You take a cable and keep on twisting it, you will see it's going to form such a structure. So if you want to model such mechanics, you have to use what's called elastic rods. Okay? Then in modeling of biomolecules, biomolecules are like long chain. It has a long chain, and the picture that you see here is an electron micrograph of relaxed and supercoiled plasmid DNAs. So DNA is also like a biomolecule, right? So these are the states in which DNA exists, and as you can see, it has got lots of looping in it. You can't use beam theory to model it, right? The picture that you see on the left, it's a schematic of the real experiment that was done in the physics department at Cornell. And what they had done was they took a strand of a DNA, as you see over there. So that's a DNA strand, and then they had an optical tweezer through which they could twist the DNA. One end of the DNA is attached to the substrate, and the other end they could twist it through some mechanism. And as you twist it, it starts forming such plectonym. And why they are doing it? Because they want to understand the mechanics of DNA. How does DNA replicate? How do cells form? So if you want to understand such things, you have to understand the mechanics of DNA. And as you can see here, you have a straight DNA here, but then it forms such loops. So this is a nano structure, right? Exists at the nano scale, but the similar deformation could also be seen with cables that you saw in the previous slide. So there is some relation as far as deformations are concerned at nano scale as well as at the continuum scale. So this is another application. Then helical perversion. Many of you must have seen plant tendrils, right? And what you see is that it will have a right-handed helix, and then suddenly it will change to left-handed helix. So that's called helical perversion. So the handedness of the helix changes. So why does that happen? So there is some stability concerns why it changes its handedness. So that has also been explained using rod theory, using elastic rods. Okay. Then of course you can model one-dimensional nanostructures like carbon nanotubes, diamond nanowire, silicon nanowire. They have got tremendous applications in nano devices. You can see there as an additives in polymers, in lithium battery anodes, reinforcements as a reinforcements in composites, nano composites, then as a probe for AFM tip, atomic force microscopy. So you have got lots of applications. You can find lot of applications. You go to Wikipedia, you will find lot of applications. And then the challenge is, how does such nanowires or nanotubes deform when some load is applied to it? So one way to do it is you just do the full molecular simulation of such nanostructures. For example, you see this carbon nanotube, it is made up of so many of atoms. So it has got lots of atoms in it. So you can do full molecular simulation of such structures, but that would be very costly. Can we not model it as a continuum? And if you can do it, then it turns out you don't need to have, the computation cost reduces tremendously. You don't need to model each individual atoms because we are not interested in them. We just want to get some gross picture. So that's where the continuum modeling comes into picture. Okay? Over here you can see buckling of nanotubes. So again, these are nanostructures, and similar modes are also found, also observed with continuum shells or continuum beams. So you see lots of similarities. Okay? I guess this is the last slide. You can find lot more. The leftmost you see curly hairs. It's again 1D continua, right? Lots of curls. You can model. There are many papers. You can go and search on Wikipedia. There are lots of papers. This is a bacteriophage T4 virus. When it attacks someone, it sends some fluid from here. And when it does that, what you see here is lower part increases its diameter, and then the diameter increase happens gradually and propagates upward. So somebody has modeled it as a helical phase transformation and used 1D theory. Okay? And then again you see here a heart. This is an artery. If you want to send a guided wire within the artery, again you have 1D continua, right? So you have got lots of applications. All right. Okay, so I hope I have been able to motivate you. Okay. All right. So that was just some nice pictures. Then we really want to get down and understand the mathematics of such theory. So this is a brief outline of the course. We begin with it's a rough outline. Okay, we will change it depending upon how we are progressing. I have written here we start. So we already did the introductory lecture. Then we have this extension, torsion, and bending of beams. But I think all of you know about this from your strength of materials course. So maybe I'll skip it. I'll see. Okay, then we talk about classical beam theories, Euler and Timoshenko beam theories. You all must have learned it, but I'm pretty sure you'll get something new. Okay? And what are their limitations? So once we understand the limitations, then we will talk about theory of special Courseraut rods. So that's the elastic rods that we are talking about, where we want to model large rotations, large deformations. Then how does constitutive law for rods look like? Moment versus curvature relationship, twisting moment versus twist, such kind of relations. Then we'll talk about modeling of one-dimensional nanostructures. So nanostructures modeled as a continuum Koszart rod. We'll talk about that. We'll talk about how the information at the nanoscale is passed on to the continuum scale. So there is something called Cauchy bond rule. We'll learn about that. Then a specific Cauchy bond rule for 1D structures. We'll also learn about that, helical Cauchy bond rule. And then we'll do some interesting examples of, or I'll demonstrate some interesting examples involving carbon nanotubes and nanowires. Okay, and if you want to do some programming, if you want to simulate it, maybe we'll have some hands-on class also. Okay, so that depends on the interest. All right, so that's a brief outline of the course. So we have 90-minute lecture, total 12 lectures. So we begin at 8:30, as Professor Steinman said in the beginning. Is that okay for all? 8:30, and then we continue for 90 minutes. We can have a break in between if you want. Do you have a course after this class? So when do you want to get free? 10 o'clock. So then we have to continue. We can't take a break in between then, right? So we do it continuously from 8:30 till 10. And then if you have any queries related to the course, you are welcome to write an email to my friends, Prakhar and Smriti, and you can also write to me. Okay? All right, very good. So that's where this slide ends. Yes.
Intervene shortly.
Sure.
So those of you who are in their master or bachelor studies, it's maybe also interesting to know that we have ample of topics at hand where we could start immediately to give out topics for master or bachelor thesis.
Yes.
That would then be supervised jointly between IIT Delhi and here, which also revolve around these kind of topics.
Yes.
A bit to the left, a bit to the right.
Exactly, yes.
So if anybody of you is currently under pressure to find a good topic and a good advisor team, yeah, then this would be maybe also a chance for you.
Yeah. Okay, thank you. All right, so can I switch it off somehow?
There, if you are interested, the black.
This one?
When it's
yeah.
black. No, then it goes off completely. You want that?
One more time?
You
or?
want to shut it off completely?
Yes.
Yeah.
Okay. All right. Okay, so now we have to get to the board. Okay.
Maybe press. Yeah.
Okay. All right, so as I was asking you, do all of you know about extension of a beam, bending of a beam, torsion of a beam? I guess all of you know about it, right? If I have to write down extension, torsion and bending of a beam, so a very famous formula, the axial force, for example, if I denote by F, axial force is then simply equal to EA times the axial strain, right? So if you are stretching a beam, I guess all of you know about this, right? So E is the Young's modulus, A is the area of cross section, and this epsilon is the axial strain. Okay. And then if I talk about bending, then bending moment M is equal to EI times the curvature, right? Very simple strength of materials things that we derive, but it's really very, very interesting. Bending moment versus curvature. And then comes the twist. Twisting moment T is equal to GJ times the twist. So how do I denote twist? Maybe I could write it as theta over L. I guess that's how we learn it in the undergraduate course, where G is the shear modulus of elasticity, J is the polar moment of area, right? Very simple. But I'll also give you some notes about extension, torsion, and bending of beams, which you can, I guess when you derive these things, you didn't really think of how the cross section is also changing. You know, for example, if I've got a beam and I pull it with the force F, then its cross section also shrinks, cross section changes, right? So some of you may have also taken that into account, some of you didn't really think about that, and just using simple formulas derive this. So the notes that I'll share, which will all actually solve the differential equations of equilibrium and derive these relations. Okay. All right. So same thing for bending moment versus curvature, twisting moment versus the twist. Okay. So assuming that we know about that, let's start with motivation for the 1D theory. Motivation for theory of elastic beams. What's the motivation? So we know about 3D elasticity. So in 3D elasticity, all of you must be familiar with this figure that we always come across. Right? How many of you have seen this? Okay, very good. So that's the reference body, and that's the deformed body. So when we model a 3D body using 3D elasticity, we talk about every point of the body. It's not rigid anymore. So, you know, each point kind of moves independently. If it were rigid, it can only just translate rigidly or rotate. But now it is deforming. So each point moves on its own. Of course, there is some relation also. So we denote any point in the reference state using capital letter, big X, okay? And since this point is lying in a 3D space, it must be a vector, right? It must be a position vector. So we have to think about how to denote vectors. So I'll use the way I learned, okay? So I'm going to use a tilde below. 1 tilde for vector. No tilde means a scalar, 1 tilde means a vector, 2 tilde means it's a tensor, second order tensor, 3 tilde third order tensor. You can keep going. It's not bad, right? Because otherwise you have to write it lightly or in boldface. If you are writing on Word, then it is fine, but if you are using your own hands, it's really difficult, right? Okay. All right. So here is the reference point, and then we have the deformed point. That's again a vector, so it comes with a tilde. All right. So this vector then is the displacement u of x and the vector that connects the deformed position. Of course, that's small x. So that means small x is equal to capital X plus u of x. Okay, and so we also know the map that brings the undeformed state to the deformed state is given by this function f, which is the deformation map, which is it has a standard name, deformation map. Then we talk about deformation gradient. Okay, so we are getting into some graduate level stuff. Which we denote as gradient of this deformation map. How many of you have heard about this? Anyone not heard about this? Deformation gradient. Okay, very good. So that's denoted by capital F, which is again a field. So it is different for different points here. So it's a function of capital X. And that's nothing but the gradient of deformation map. So gradient again, it's a vector gradient, so it has to come with a tilde. Okay, and gradient of small f, and the gradient is being taken with respect to the undeformed coordinate. So you have to show that here with respect to capital X, not with respect to little x, because this is Lagrangian, isn't it? Okay, so these are some terminology which you will come across later on. And let me just write down the equations of equilibrium that you also see, equations of equilibrium. So if you are talking about the Eulerian equation, then that's the divergence of Cauchy stress tensor. You see the stress tensor sigma, all of us use this sigma, right? So it comes with two tildes because it's a second order tensor. So it comes with two tilde, divergence dot sigma. Divergence acts on a second order tensor and brings down the order of the tensor, and it becomes a vector. Divergence always brings down the order of whatever it is acting on, plus the body force B is equal to rho times acceleration, right? Anyone not seen this? Okay, very good. But you can be very frank with me. I'll go very slow. Okay. So that's the Eulerian equation. And if you want to talk about the Lagrangian form of the equation, then that is again divergence but with respect to capital X, not little x, capital X dot, not the Cauchy stress, but the first pk, right. So, I will use P plus the body force. So, I write here big B, because this is body force per unit undeformed volume, whereas that is the body force per unit deformed volume. Okay, so, they are two different things. And on the right hand side I have rho naught times the acceleration. And acceleration looks really simple in Lagrangian. So, you could just say del 2 f by del t 2. Rho naught is the undeformed density, whereas this is the current density rho, Eulerian Lagrangian. So, that is the Lagrangian form. Okay, just a recap of the 3D elasticity. You do not really need to know it in a great detail for this course. So, here we want to talk about every point here. That is why the equations that we get are partial differential equations. They are PDEs in 3D space. So, we get PDEs in 3 independent variables x1, x2, x3. It is a 3-dimensional body, all right, because every point here moves independently, all right. Okay, so I got this. Okay, so that's about for any, so that's a general theory. You can use that even for 1D beams, but it's really complicated, right? It's a, what we have to solve is a PDE in 3 independent variables. But often, and of course, it's complicated to solve, but you get a very nice information about every point in the body, accurate information about the deformed position of every point in the body. But often you have body which are very slender. That is the one we are going to focus here. So, you know, something like this. Slender body whose L by D, for example, the length L over the diameter D, and it not be circular, it could be rectangular also, then some representative lateral dimension would be D. So, if L by D is, you know, greater than 10, for example, so we call them slender bodies, slender. And then again you apply your 3D elasticity here. So, it is going to deform, and then it might look like something like this. Right, it could be something like this. But the thing is, it is very slender, and we may not be interested. It is possible that we are not interested in knowing about every point here. We might be happy with just knowing the center line, for example. So, let us say we have the center line here. you can also see here, if you somehow know the center line, you can construct the full deformed body in an approximate sense, not exactly, but in somehow approximately, right? You know the center line, then just put your cross section here and get your body. But of course, you don't know how the cross section looks like finally. But if you really look at the things in nature, if it is cylinder and you deform it, just see this cable, for example, it's very cylinder, you deform it whatever way you want, what's happening to its cross section? Nothing really. I mean, nothing is really happening here, right? Something is happening, but very little compared to the deformations along the axis. So that's why bother about knowing the every point of the body? Why not we just be happy with knowing the center line? So if you are happy with that, then that's what the 1D theory is about. Okay? So this is the mechanics of center lines. The 1D theory is nothing but the mechanics of center lines. And of course, then there are some advanced versions of 1D theory where then when people start talking about, okay, just knowing the center line may not be enough, why don't we also know about the orientation of the cross section? You know, this cross section, for example, over here, how is it oriented? You might be wondering, if I know the center line, I draw the tangent here, and then this must be normal to the cross section, right? Approximately, isn't it? But if you want to be very, very accurate, sometimes it is not. So then the center line and the orientation of the cross section can be thought of as two independent unknowns, and then you get more, you know, refined 1D theory, you can say. So 1D theory here, so you have mechanics of center lines plus the orientation of cross section, and you can include more and more, plus orientation of cross section. So this theory, the first theory was just the center line. That's also a good theory. If you want to be more accurate, you bring in this orientation. If you want to be even more accurate, you can bring in some more variable, and you get even more accurate 1D theory when you compare it to the 3D theory. But then you see you are bringing in more and more unknowns. But the nice thing about this theory is that the unknowns, for example, the center line that you see here, any point over here, so you take it and bring it over here. Maybe I should use another chalk. So if I denote center line with a small r, and let's say the coordinate along the axis here is little s, okay? S denotes the coordinate along the axis, arc length. So for a given s, you get a cross section. You fix one s, you get one cross section, fix another s, you get another cross section. So here you have small r of s. So that tells me where is the center of this cross section when it has gotten deformed. So the unknowns are a function of only one independent variable S. So center line given by small r of just S. And orientation, you will see later on, could be denoted by rotation, for example, right, a rotation matrix. So this could be denoted by a rotation tensor. Don't worry about it, how does it look like, but it's just some rotation, which is again a function of only S, just arc length. So the unknowns, all the unknowns here are just the functions of one independent variable. Compare that to the 3D theory. What is the unknown here? Little x, or the deformation map. And the unknowns are functions of capital X, which is itself a, it's a vector. So it has got three components, x1, x2, x3. So unknowns there are functions of three independent variables. That's why the equation that you get to solve is a PDE. But over here, the unknowns are only functions of arc length, just the S. And you will see that the equations that you get are actually ODEs. So the equations that you need to get these unknowns are just ODEs. So equations to solve are simply ODEs. Which can be obtained by averaging the equations of 3D elasticity in the cross section of the beam. So don't worry how it is done. So right now I am just telling you a broad picture. So the equations to solve the ODEs, so they can be obtained by integrating 3D equations in beam's cross section. So we do averaging of the cross section. So in that way, we actually are shrinking the cross section to a point on the center line. So we forget about what's happening to cross section, and everything is shrunk to a point on the center line. So that's why it's mechanics of center line. Okay. And you see, so what's the advantage? What you have is an ODE to solve for, compared to PDEs. ODEs are much easier to solve for, right? And you can also do some paper and pencil work. So that's another nice thing. Okay. So that's the motivation. Yes. Put it up? Yeah, I'm going to put it up. Prakhar, can you erase this? Okay. Oh, you have to be careful here. Okay, so yes.
Why do we have a rotation matrix, and why Why we couldn't have another vector to identify the normal of this cross section at S?
Yeah, it turns out so rotation matrix is actually an orthogonal matrix, proper orthogonal matrix. So it has only 3 independent variables actually. So there are many ways to represent rotation. So it's like a vector. Yeah.
The example in 2D is the structure that you know, like cosine, sine,
Yes.
minus sine, cosine.
Right.
The extension to 3D is a bit more involved.
Is a bit more involved, yes. Yeah, so in the 2D case, for example, if you're just talking about planar deformations that we'll talk about now, the rotation is given by a single variable theta, scalar variable theta. So we'll just talk about that. Okay, any more questions? Okay, very good. So having done the motivation, we now want to talk about the theory of, well, the Euler-Bernouli beam theory. Euler-Bernouli beam theory. And then we'll talk about the Timoshenko beam theory. Okay, so we saw that it's just a mechanics of center line. So we have, let's just focus on the center line. So over there we had the cylinder or a cylinder body. Let's shrink it to its center line, a straight line. Okay, so we just have a line here. And let's just focus on 2D deformation. So this line deforming in just the plane of the board. Let's not focus about the 3D deformation. It's the simplest case, and Euler-Bernoulli is actually that. So planar deformation, planar case. So you just have 2 axes. One of them could be x and the other one could be y. So here is the straight beam. It gets deformed and it could become something like this. So this is just a curve. So you could denote it as any point over here is some y of x. Right, it's a curve. So mathematically you can represent it as y of x. Then we think about what's the curvature of this beam at any point. If you have got a curve, what's the curvature? So if I denote that by kappa, then the curvature kappa as a function of x is d2y by dx2 over 1 plus dy by dx whole square to the power 3 by 2. That's the curvature. Okay? And all of you know from the elementary strength of materials that curvature is related to bending moment, right? Very simple formula. Bending moment m of x is equal to EI times the curvature. Yes.
I suppose it would be helpful for most of the people to recognize that under certain assumptions, the equation that you see there for the curvature, if expressed in terms of the deflection, and then assuming small deformations, would simply be minus second derivative of the deflection, and then You have the formula that you know from your strength of materials.
Okay, yeah. So
it's like an extension
yes.
that takes into account the geometry of the fine forming line.
Yeah, I'm actually going to come to that too.
Sorry.
Okay. So you see, this is the general formula for curvature. This is non-linear in the deflection y, right? Y is the deflection, isn't it? So this is non-linear in the deflection y, which means if you double the deflection, curvature does not get double. So it's non-linear. Now why don't I put that accurate formula for curvature over here and see what do I get. So that tells me EI d2y over dx2 over 1 plus ty by dx whole square to the power 3 by 2 is equal to the bending moment x. So this is how your, so you see you have an equation for the deflection y. This is 1D theory, right? We just want to know the deflection. If we just want to know the center line, that's the equation. This is a ODE because it's only in the unknown x, and y is the unknown variable. So it's an ODE, but of course non-linear ODE. But the equations that you have seen perhaps for Euler-Bernouli is not the same. So of course that means we have to apply some approximation. So the approximation that you have to apply, or that people apply, is that okay, because we want to get rid of nonlinearity, you see the nonlinearity is in the denominator, so we are going to say that dy by dx is very, very close to 0. Okay, so let's apply approximation. See, because all of you have learned this, so I can start with slightly advanced presentation. If you hadn't learned it, I would have to start with an approximation, but because you have learned it, I have the liberty to do this. Okay, so the approximation is that dy by dx is very, very close to 0. And what does that mean physically? So dy by dx is nothing but the slope of the curve. So that's a slope. And if this is theta, then dy by dx is nothing but tan theta, which is equal to tan theta. And we want to get rid of nonlinearity, which means I want to make it close to 0. Or you could also say it is much, much less than 1. Okay? So which means, when can this happen? Tan theta much, much less than 1, when does that happen? So this implies actually, right? So I have to write that this implies theta is small, right? See, that's what I had been talking about. If theta is large, you can't use this theory. So theta is small. So let's see what happens when you apply that. So this means EI d2y over dx2. So see, the denominator becomes 1 because dy by dx is much, much less than 1. So its square will be even less than 1. See, if dy by dx is 0.01, its square is 0.0001. It's very small compared to 1. So you forget about this. So you only have the numerator. And you see now you have a linear equation, right? it's linear in the deflection y. Of course, you might be bothering what about this moment m of x. So, we will solve some problems and see how do we get this bending moment profile, for example. So, that is the Euler-Bernouli equation. Euler-Bernoulli equation. At this point, I should also tell you that as we saw here, that dy by dx is actually, if it is very, very less than 1, dy by dx is same as theta, right. So, now in this theory you can say that dy by dx is same as theta, but which theta? This is the theta of the centerline tangent. Is it same as the theta of the cross section? So, see, there are two things here, as you see over here. So, that is the curve, and then you also have the, so this is the tangent, and if you want to build the rod or build your beam, you have to put the cross section. So, if you put your cross section like this, then the normal to the cross section is not the same as the slope, isn't it? So, in Euler-Bernoulli theory, it is assumed that the normal to the cross section is aligned along the tangent to the center line. So, we can't have this in Euler-Bernoulli theory. So, all that you can have is you have to put it like this, so that the normal is along the center line tangent. Okay, so this theta has got two meanings. It is same as the slope of the center line, and also the cross section normal. Okay. Yeah. Any question? Okay. Yeah.
We have this example for the nonlinear equation of how much moment you have to apply to transform an original straight beam of length L into a circle, because that is a very easy solution to the nonlinear equation.
Yes, it's very, yeah, we'll have that, of course, but only when we are done with Euler, Bernoulli and Timoshenko, because the curvature is very large there, right? That's not going to work. Okay, I hope you are not getting bored. Is it very simple stuff? Of course, today it might be simple, but as you progress, you will get hard and hard things. But you may not like that also. Yes. Can you say again?
As you showed there, we have different points, and different points have different angles,
Yes.
right?
Yes.
How can we make sure that all of the points have very smooth difference?
Well, you can't make sure about that. You just assume that. One of the ways to do it is you apply very less load. So you have got a beam. Let's say you have a cantilever beam. If you apply very less load, the deformation will be very small. Then automatically every point will have very small slope. Otherwise, I mean, you can't always say when every points have small deformations. You just assume it beforehand. Okay, assuming that every points have got very small deformation, let's apply Euler-Bernouli theory. But in a broad sense, you can say that if the load is very small, then that condition will most likely be satisfied. Yes. Okay. All right. So let's solve a very simple problem, which is the deflection of a cantilever. So here we've got a cantilever which is clamped at one end, but there is a transverse load acting at the other end. Okay, and we want to solve it using Euler-Bernouli theory. So as you see there, that equation is second order in the deflection y. So if you want to solve that ODE, how many boundary conditions do you think you will need? Yes? 3. Why? 2 boundary conditions. So depending on the order of the differentiation, so if it is second order, you need 2 boundary conditions. Provided you know the bending moment profile, provided you know m of x. And if it is that you can't get m of x, if there are some unknown constants in the bending moment profile itself, then you have more unknowns, so you would need more boundary conditions. Okay, I'll show you one example. So in this case of cantilever, what do you think? What boundary conditions we are supposed to use?
Slope is 0.
Slope is 0?
Yes, and y is also 0.
Exactly. So y of 0 is equal to 0, and slope is also 0, and slope is given by dy by dx, right? Slope, so dy by dx at 0 is also equal to 0. And how about m of x? What will be m of x? So if this is your x, and I want to know the bending moment in this cross section, how do you get that? So you just draw this separately, draw its free body diagram. Here is your P, and then you have shear force V of x and bending moment m of x. So this is a convention. So this cross section has its normal in the negative direction. Okay, so its normal is in the negative direction. Therefore, on this cross section, shear force going downward is positive, and bending moment clockwise is positive. If you talk about the other part of the beam,
You use the y upwards?
yes, y upwards. So if you talk about the other part of the beam, now this cross section has got its normal in the positive direction. So shear force upward is positive, and bending moment counterclockwise is positive. Okay, they have to be action reaction pairs, right? So that's the convention. All right, so if I look at this, then I do net force balance, because this part, any part of the beam has to be in equilibrium. You apply force balance, that gives me V of x is equal to P. So shear force everywhere is P. And then if you want to talk about the moment balance, then you get negative m of x, because it is clockwise, plus the moment due to this P. So let's do moment balance about this point over here. So this is negative m of x plus moment due to P, which is P times L minus x, because this is x, so this part is L minus x. Okay, very simple. So this tells me that m of x is equal to P times L minus x. So you see, you got the moment profile, there is no unknown, so we are safe. So we need only two boundary conditions, which you already have, right? So going back to that equation, d2y over dx2 is equal to P over EI times L minus x. So that implies you can integrate it twice, and you get y of x equal to P over EI times, can someone tell me what's this going to be? L into x square by 2, because you are integrating a constant twice, you get x square by 2, minus x square by 2, then x cube by 6, right? So it becomes x cube by 6. You just have to integrate this, but then you also get two integrating constants, plus c1x plus c2. Okay, so very simple, and you will see we are going to use this equation later on to demonstrate when to use Euler-Bernouli and when to use Timoshenko. So although a very simple case, but the final equation here we will use that later on. Okay, so then we apply the boundary condition, y of 0 is equal to 0, x equal to 0, put in, this goes away, this goes away, this goes away, this remains, that means this is 0. Then you apply dy by dx at 0 is equal to 0, you take the derivative, this will become x, this will become x square by 2, evaluate that at x equal to 0, gone, gone, this becomes c1, so it is a constant, but it has to be 0, so this also goes away. Okay. All right, so the deflection that we get is y of x is equal to P over 2 EI, maybe let us put L also here, P over 2 EI, PL over 2 EI times, or we could do x PL cube over 2 EI times x by L whole square minus 1 over 3 of x by L whole cube. Okay. All right, so very simple problem. Let's do a little complicated problem. We again have the same cantilever. and it's acted by a force P, but it has slight complication that it's not allowed to rotate here. Okay, so rotation is restricted here somehow. So then what happens? Now I want to solve it. So what boundary conditions do I have? The other end, the clamp end, is same as it is over there. So we have y of 0 equal to 0, dy by dx at 0 is equal to 0. So looks like we can still solve it, but then you have to relax and see, okay, can I get the bending moment profile? So if I want to get bending moment at any cross section x, what should I do? Let's cut this section. So this is at x. We again have the shear force V of x and bending moment m of x. But what about this end? What do I have over there? We have got a force P. Is there anything else?
Moment that enforces this cross section to be bent.
Yes, because the rotation is not allowed here, it is restricted. So the only way to restrict the rotation is by applying some moment. So there will be some reactive moment here, some m naught, but we don't know that. So that's an unknown. Okay, so when you write down your bending moment profile, then you have m of x equal to m naught plus p times L minus x. Okay, so you see you got one more unknown here, unknown, and you will of course get two more unknowns when you integrate the equation. You get two integrating constants, so two unknowns there, another unknown over here, three unknowns. But we have two boundary conditions. We have to look for another. Can you find it? Right, it's very simple. So the third is that dy by dx at L is also equal to 0. So you use three boundary conditions and integrate, you get the three unknowns, you get the deflection. Okay. All right, so let's just put it up. So you see, you could solve that problem. At the end of the class, if I have time, I'll talk about a problem which will look very simple, but we won't be able to solve it using Euler-Bernouli theory or using Timoshenko-Wien theory. It will look very simple. Okay, so you have some interesting thing coming up. Sorry, where is my page? So, it's very tricky to find out the boundary condition. It's not so easy. So, I am going to just write down some rule of thumb which you can use to know what boundary condition to use and what not to use. So, you see, if displacement is prescribed, if it is prescribed, that would mean that force would be unknown. For example, in that particular case, at the left end, y of 0 is equal to 0, it is prescribed. So, force, we do not know what the force is. Of course, you can get it by solving or by equilibrium, applying equilibrium, but before applying equilibrium, you do not know it, right. So, if displacement is prescribed, force is then not known. So, this would be your boundary condition, and you can do it for all three directions. You see, in that case, displacement is prescribed in that direction, in this direction, as well as in that direction, in all three directions. So, force is unknown in all the three directions. Same thing goes for, now if force is prescribed, then displacement would be unknown. You look at the right end of the cantilever, force is prescribed, but we do not know the displacement. You get that only after solving the equation, right. So, you have to use this as a boundary condition. So, you will always have either displacement or force prescribed. Then we talk about rotation. If rotation is prescribed, then moment will be unknown. Look at the next problem. Rotation was prescribed and equal to 0 at the right end, but the moment over there was unknown. So, you have to use whatever is prescribed as a boundary condition, whatever is known. So, you can use rotation at that end as a boundary condition. And if rotation is, sorry, if moment is prescribed, then this will be unknown. Okay, so, that is a very simple table. All right, so that is about Euler-Bernouli theory, and you saw the limitations. See, the main thing was to demonstrate the limitations. See how you brought down the curvature, you got rid of the nonlinearity and made it equal to d2y by dx2, and other things were just to refresh your memory, I guess. Okay, so then we talk about Timoshenko beam theory. So, if you remember, in Euler-Bernoulli theory, the center line tangent and the cross section normal were aligned, but we relax that in Timoshenko beam theory and we say that they are independent. Center line tangent is not the same as cross section normal. So, we make both of them as independent. So, as you saw, so now it is the mechanics of center line plus the orientation, a more refined theory. So So how can we come up with? So we have to have two equations then, right? One for the deflection, y, another for the cross section orientation. So we need to have two equations. So how can we get the two equations? Okay, so what we could do is we again have our center line, and then this is the center line tangent, and the cross section could become like this, because it is no more aligned along the tangent. So cross section normal is this. Okay. So then we have to look at these lines more carefully. So how were those lines before deformation? Before deformation it was straight, and if I talk about this line and this line, for example, so I have the cross section before deformation, that's the tangent, and that's a line in the cross section. Cross section line. And after deformation, you see what has happened. So the tangent goes like this, whereas the other line, maybe I can use the, okay, so let's use this. And those were the initial directions. What do you think about this? What is that angle equal to? So this is the tangent. What is that angle from the horizontal? That's the slope of the center line, right? And what's that equal to? dy by dx, right? So, well, so this is dy by dx. Okay, very good. Assuming that the rotation is still small, otherwise it is tan inverse of dy by dx. So we are assuming again that rotations are small. So this is dy by dx. What about this angle? What do you think that angle is equal to? So that's the rotation of the cross section, right? So now let's introduce another variable for rotation of cross section as theta. So theta is no more same as dy by dx. So that's the cross section rotation. You see the cross section rotated by theta. Now in this picture I have drawn it as a clockwise rotation. So I'll have to use negative theta here. Okay, so this is negative theta. Now, can you say about what happens to the angle between these two lines? You see, the yellow line and the red line, they were initially perpendicular. Now, the angle between the two lines have changed. What has that become? So, you see this is negative theta, that is dy by dx, and the whole thing is 90 degree. So, what is the final angle? What is this angle? Pi half minus dy by dx. Is that plus theta? Minus theta, okay. So, what is the change in angle between the two lines? Initially it was pi by 2 and finally it has become this. So, the change in angle is dy by dx minus theta, which we know from linear elasticity is same as the shear strain, right. So, shear strain that is gamma is equal to dy by dx minus theta, right. Now, you see this was all being done at the center line. So, we had the center line we have cross section and its center here. So, we were looking at two lines in the cross section, but at the center. Now, what will this shear strain be in terms of shear force? Can you think about it? What will be gamma in terms of shear force from elementary strength of materials? So, gamma is equal to shear stress by G, right, tau by G. So, this is same as tau shear stress over G. Now, what is the shear stress at the center of the cross section? So, you have a shear force V acting in the cross section, right. In the cross section, the shear force that is acting is V, and if you assume that it is uniformly distributed over the cross section, then the shear stress is V by area, right. But then you know that it is not uniformly distributed. Do you know this? Right. So, what's the shear stress then at the center? So, you have to introduce some correction factor, and then this becomes, so shear stress will be V shear force divided by area, and then it also comes with a correction factor kappa. Okay, I have already a kappa, so maybe I should use sorry K, just a K, okay, K, and then this G comes in the denominator. So, this becomes V by K G A. Okay. So, that is your equation. So, the equation that we have found out is that dy by dx minus theta is equal to V of x over K G A. So, this is also a function of x, and that is also a function of x. Now, what about the other equation? Does it remain the same that we have in the Euler-Bernouli? So, what should that be? Should that be EI d2y by dx2 equal to bending moment m, or should that be something else? Because you see dy by dx is not the same as theta here anymore. So, what does that become? Well, that's what, so that's very tricky. It's really, really tricky. What should it be? Should it be d2y by dx2, or is this, should this be the, should it still be the curvature of the center line, or it should be something else? That's not so easy, I can tell you that. And that's actually d theta by dx. And how is that so? We'll have to do some derivation for that. This is really not easy as far as I know. Well, some of you can just write it down, but if you want, if you sit back and think about why is that so, it won't be easy to derive. So that's something we will derive it, but I guess we already have, it's already 10, maybe should we postpone it then?
I think it's a good point to stop here. No?
Yeah. Okay, yeah, I'm also tired a bit.
Okay, maybe we should just remember that we proceed Tuesday then?
Yes, Tuesday,
8:30.
8:30.
Again, if some of you are interested to pursue a thesis, just approach either Professor Kumar or myself. And then you've seen that the whole lecture is videotaped. So I guess with a little delay it will be available on the video portal of the FRU.